Have you ever examined whether we're really alone in the universe? Or is there something more to our world than what we see? Imagine if the James Webb Telescope finally reveals that we live inside a black hole. Join us as we explore this crucial news that will make you question everything you thought you knew about the universe. So, what exactly are black holes? They're like something out of a terrifying nightmare. Sure, you might have seen them in sci-fi movies, but they are much more frightening in reality. Black holes are not just fictional, they are real as confirmed by experts. Essentially, black holes are enormous amounts of matter squeezed into an incredibly small region. Picture a star many times more massive than the Sun, all compressed into a sphere the size of New York City. The gravitational pull is so intense that nothing, not even light, can escape from it. Scientists have been fascinated by black holes for quite a while. These objects in space are so massive and dense that they can trap light. The most well-known theories about black holes were predicted by Einstein's theory of general relativity. Essentially, when a massive star reaches the end of its life, it collapses, leaving behind a dense core. If the mass of this core is many times that of the Sun, gravity overwhelms everything, leading to the formation of a black hole. It's not easy to detect black holes, as they don't emit any light. However, scientists have found ways to infer their presence by observing their effects on nearby matter. For example, if a black hole moves through a mass of interstellar matter, it will pull that matter toward it in a process called accretion. Additionally, when a normal star gets too close to a black hole, it can be torn apart, emitting X-rays as it does. Black holes also have a huge impact on their environments. They can consume nearby stars, emit powerful gas blasts, and even influence the formation of new stars in some regions while slowing it down in others. But where do black holes come from? Imagine stars, once massive and vibrant, meeting their tragic end in a dramatic event known as a supernova. From the remnants of these fallen giants, black holes are born. Most black holes originate from massive stars that end their lives in a supernova explosion. Smaller stars, when they die, transform into neutron stars, which are incredibly dense but not dense enough to trap light. If a star is several times the mass of our Sun, it collapses under its own gravitational force, forming a black hole. As these collapses occur, something strange happens near the surface of the black hole. Time itself begins to behave unusually. From the perspective of someone far away, time appears to slow down near the event horizon, the point beyond which nothing can escape. It's as if the star's clock ticks at a different speed compared to our own. Sometimes, when two smaller black holes collide, they merge to form a much larger and more terrifying black hole. If a black hole interacts with a neutron star, it creates a massive nightmare that defies comprehension. Scientists have struggled to comprehend the scale of these immense phenomena for quite some time. Black holes come in two sizes, big and small. But here's the twist. Small is relative when it comes to black holes. Very large black holes, the remnants of massive stars, can be as large as 10 times the size of the Sun. There could be up to 10 million to a billion of them in the Milky Way alone. That's a staggering number of black holes that could swallow anything in their path. However, there's something even more enormous on the far end of the spectrum: supermassive black holes. These can be millions or even billions of times larger than the Sun, and they exist at the center of large galaxies, including our own Milky Way. It's like a vast, dark void, pulling everything toward it. Famous physicist Stephen Hawking spent much of his life studying black holes. His lectures were always insightful, though some of his theories couldn't be confirmed due to a lack of necessary equipment. But there is hope on the horizon, and it comes in the form of a single scientific instrument: the James Webb Space Telescope, or JWST. This telescope is here to delve into the depths of our universe. The JWST is no ordinary telescope. It's an engineering marvel, a testament to the power of human ingenuity. While other space telescopes have done their jobs well, the JWST is in a league of its own. It makes the Hubble Space Telescope look like a simple speck in the vastness of the universe. The cost of this cosmic miracle? A staggering $10 billion. A number so large it's hard to fathom. This incredible project was the result of collaboration between NASA, the European Space Agency, and the Canadian Space Agency, with contributions from over 300 universities. However, it's not just about the money, it's about the risks involved. The JWST is venturing into uncharted territory, pushing the limits of our knowledge and taking us to places we've only dreamed of. After a successful launch, NASA recently announced that the telescope has enough fuel to last more than twice its base mission life. Since its launch, the JWST has accomplished numerous incredible feats. It traveled more than 1 million miles to reach its orbit around the Sun, where it will remain for eternity. During its journey, it successfully deployed its massive 5-layer sunshield and giant primary mirror, both of which had to be folded to fit into the launch vehicle. Now, after NASA has aligned and calibrated the telescope, it is nearly ready for full operation. One of the most fascinating moments came when NASA announced it had captured its first images of starlight. The first picture taken by the telescope was of a star called HD 8446, which resulted in a mosaic of 18 scattered bright spots from the star's light, captured by the 18 mirror segments on the primary mirror. Later, NASA released another stunning image of HD 8446, where 18 unfocused copies of the star were combined into a purposeful hexagonal arrangement. Once the observatory aligns the individual segments of the primary mirror, it will begin the process of stacking the images, merging them into one clear view. Thanks to its cutting-edge technology, the JWST will assist researchers in studying the early stages of the universe, particularly the period following the Big Bang. It will help scientists investigate what happened after the first stars formed, a time known as the epoch of reionization. This refers to when neutral hydrogen was reionized, or made electrically charged again by radiation from the first stars. This is only possible with a powerful telescope like the JWST. The telescope will also aid in the discovery of exoplanets, which are difficult to identify due to their interaction with their host stars. The powerful sensors of the JWST will be able to observe these planets in more detail, and in some cases even image their atmospheres. Understanding the atmospheres of these planets could help scientists predict whether some of them are habitable. In addition to studying planet formation, scientists are studying galaxies to understand how matter is organized on a large scale. This will help us understand how the universe evolved and how galaxies like the spiral and elliptical galaxies we see today developed from different shapes over billions of years. One of the JWST's goals is to look back at the earliest galaxies to better understand this evolution. Researchers are also trying to figure out how we ended up with the variety of galaxies visible today and how galaxies continue to form and evolve. Most significantly, the JWST will help answer some of the biggest questions of all. Are we alone in the universe? And are we living inside a black hole? The JWST has already made some intriguing discoveries. For example, it found compounds called polycyclic aromatic hydrocarbons, PAHs, around supermassive black holes in 3 active galaxies. These carbon-based molecules, with their ring-like structures, are like the goth kids of the universe. They're found everywhere, from distant galaxies to comets, and even in our own solar system. PAHs are not only interesting because they could be the building blocks of life, but also because they help astronomers track star formation. When ultraviolet radiation hits these PAHs, they glow and emit infrared light, a signal detectable by the JWST's mid-infrared instrument, MIRI. This typically indicates the presence of hot, young stars nearby. However, there's a twist. A curious astrophysicist, Ismael Garcia Bernard from Oxford University, decided to investigate 3 active galaxies, NGC 6552, NGC 70319, and the famous Stephan's Quintet. These galaxies are millions of light-years away, buried in the darkness of space. What Garcia Bernard found will make your hair stand on end. In the central regions of these galaxies, where the black holes dominate, he found a ton of PAHs. Sounds great, right? Well, here's where it gets eerie. The radiation near those supermassive black holes distorted the PAHs, transforming them into larger, electrically neutral versions of themselves. The smaller, electrically charged PAHs vanished into the void, consumed by the darkness. Now, imagine being consumed by that darkness. But wait, there's a glimmer of hope, or maybe not. The real question isn't whether we're alive, but whether we truly exist. Does everything around us exist because of the black hole we reside in? Everything could be connected within the theory that maybe we're not just living inside a black hole, but rather inside its event horizon, the boundary between the known universe and the unknown. Could it be that everything is part of a black hole? The James Webb Space Telescope is out there, searching for answers to these unknowns. Stay tuned, and maybe, just maybe, it will make us rethink everything we thought we knew about existence. The truth could be far more twisted than we realize. In the fascinating world of astrophysics, few topics have generated as much intrigue and wonder as black holes. These enigmatic entities, once the stuff of science fiction, have captivated the imagination of scientists and the public alike. As scientists continue to explore the mysteries of the universe, black holes remain one of the most perplexing phenomena in astrophysics. The concept of a black hole was first introduced in the 18th century by the English natural philosopher John Michio, who speculated that objects with a gravitational pull so strong that even light could not escape them might exist. However, it wasn't until Albert Einstein's theory of general relativity in 1915 that black holes were mathematically predicted. These regions in space where gravity is so intense that it distorts space-time itself have since been the focus of extensive study, and every discovery about them seems to lead to even more questions. One of the most fascinating aspects of black holes is their event horizon, the boundary beyond which nothing, not even light, can escape. The event horizon marks the point at which the gravitational pull becomes overwhelming, and this region is often described as a point of no return. Anything that crosses the event horizon is inevitably drawn toward the singularity at the center of the black hole. The singularity, a point of infinite density, is where our current understanding of physics breaks down. The equations governing general relativity no longer work under the extreme conditions inside a black hole, and the mystery of what happens within the singularity remains unsolved. The study of black holes has revealed an interesting paradox. While black holes can swallow matter and light, they also emit radiation, a phenomenon known as Hawking radiation, predicted by physicist Stephen Hawking in 1974. This radiation is the result of quantum effects near the event horizon. According to quantum theory, particles and antiparticles constantly pop in and out of existence in empty space. Near the event horizon, one of these particles may be captured by the black hole, while the other escapes, carrying away energy. Over time, this process causes the black hole to lose mass, potentially leading to its eventual evaporation. However, this radiation is incredibly faint, making it nearly impossible to detect with current technology, and its effects are negligible for black holes with masses much larger than the Sun. Interestingly, despite their name, black holes are not empty in the traditional sense. While they do not emit light, they interact with their surroundings in powerful ways. When matter falls into a black hole, it forms a hot, glowing accretion disk of gas and dust. As this material spirals in toward the black hole, it heats up due to the immense gravitational forces, emitting radiation across the electromagnetic spectrum, from X-rays to radio waves. This accretion process allows scientists to indirectly observe black holes, even though they cannot be directly imaged. In some cases, astronomers have used this radiation to map the environment around black holes and even measure their size and spin. Moreover, black holes can also produce powerful jets of energy, known as relativistic jets, which can extend for thousands of light years. These jets are thought to be formed by magnetic fields generated by the spinning of the black hole and the surrounding accretion disk. As charged particles are accelerated along these magnetic field lines, they can be ejected at nearly the speed of light. These jets are often observed in active galactic nuclei, AGN, where supermassive black holes reside at the center of galaxies. The energy and material expelled from these jets can have a profound impact on the galaxy, influencing star formation rates and the evolution of the galactic structure. Recent advancements in technology, especially with the launch of the James Webb Space Telescope, JWST, are allowing scientists to probe the farthest reaches of space and investigate black holes in unprecedented detail. The JWST's infrared capabilities allow it to peer through cosmic dust clouds and observe objects too faint or distant for other telescopes to detect. This will help scientists understand how black holes grow and evolve over time. Observations of distant galaxies and the supermassive black holes at their centers will provide critical insights into the formation of these cosmic giants and their role in shaping the universe. Another exciting aspect of black hole research is the idea that these mysterious objects could hold the key to understanding the nature of quantum gravity, a theory that seeks to reconcile general relativity and quantum mechanics. At the heart of a black hole, the singularity represents a point where both quantum effects and gravitational forces are extreme. Studying black holes may offer clues as to how to unify these two fundamental theories of physics, which currently operate under different sets of rules. Furthermore, the study of black holes challenges our very understanding of time and space. Near the event horizon, the fabric of space-time is so distorted that time itself is stretched. This effect, known as time dilation, means that time flows more slowly for an observer near the black hole compared to someone far away. If an astronaut were to fall into a black hole, they would experience time differently than someone observing from Earth. This strange aspect of black holes highlights the mind-bending possibilities of space and time, pushing the boundaries of our understanding of the universe.